This video explores how restricting molecular conformational flexibility resolves delayed emission quenching, doubling OLED external quantum efficiency, or EQE. TADF designs rely on through-space charge transfer. We investigated this with secondary donor TPA and acceptor TRZ, bridged by a secondary donor. The flexible DMAC bridge allows conformational flexibility, while the rigid PXZ bridge offers a planar structure that physically separates the donor and acceptor. In nonpolar MCH, the rigid PXZ TPA TRZ shows a single predictable emission band. Conversely, the flexible DMAC TPA TRZ exhibits two distinct emission bands: a high-energy DMAC TRZ CT state at 420 nanometers and a lower-energy TPA TRZ CT state at 525 nanometers. Time-resolved fluorescence spectroscopy shows the high-energy blue band decays quickly, in less than 10 nanoseconds. This suggests quenching via intramolecular energy transfer to the lower-energy CT state. The low-energy band, however, persists and redshifts over 200 nanoseconds. Quenching requires physical reorganization. Freezing the MCH solution to 120 Kelvin suppresses the low-energy emission and hinders the formation of the 485 nanometer CT state. This confirms that thermal activation and geometric reorganization are needed for the molecule to fold and quench the emission. DFT conformer searches show that the sp3 hybridized carbon in DMAC allows two states. Conformer 1 is continuous and flat. Conformer 2 is distorted and folded, forcing the TPA and TRZ units to fold cofacially with a 138-degree bending angle. The folding is driven by strong dipole-dipole attraction between the TPA and TRZ units, forcing a ground state cofacial dimeric species. Non-covalent interaction mapping confirms strong van der Waals interactions lock the TPA and TRZ planes into a cofacial heterodimer. This folded intramolecular dimer trap introduces a large singlet-triplet gap of over 0.2 electron volts. This acts as an energetic roadblock, effectively quenching reverse intersystem crossing, risk, and eliminating delayed fluorescence. Replacing the flexible DMAC with the rigid phenoxazine bridge, PXZ, completely prevents DA folding. The planar PXZ core forces a highly twisted DA conformation that keeps TPA and TRZ separated, preventing cofacial alignment. Since PXZ TPA TRZ cannot fold, it maintains a pure, decoupled CT state. This results in an incredibly small singlet-triplet gap of about 0.03 electron volts, facilitating highly efficient risk and robust delayed fluorescence with a high risk rate. To confirm that preventing excited state reorganization impacts real-world applications, both flexible and rigid emitters were integrated into identical OLED architectures. The rigid PXZ TPA TRZ emitter significantly outperforms its flexible DMAC counterpart. Preventing dimer-induced quenching translates to a massive leap in luminous efficiency and EQE. PXZ achieves 22.0% EQE compared to DMAC's 10.5% EQE. The performance leap driven by bridge rigidity is consistent across all major electroluminescent parameters. PXZ yields near 100% PLQY and massive gains in current and power efficiencies, resulting in a more than 2 times performance increase. The key takeaways for next-generation TADF design include: beware of asymmetry, as dipole-dipole attractions can trigger ground state reorganization and folding. Bridge rigidity matters, as sp3 hybridized flexibility allows cofacial folding, and controls spatial dynamics to guarantee efficient risk. The source for this research is the article, Intramolecular Dimerization Quenching of Delayed Emission in Asymmetric DDA TADF Emitters, published in the Journal of Physical Chemistry C.